I have like more contact with the air, and the change in temperature of the air, uh, like produce it has an effect on my lungs.
Oh, so you need to be careful with your dressing. Like if you are biking, so you need to cover yourself a lot, even if you it is hot. I think so. So study we were talking about the regularity of the heat equation, and we have pretty much idea about the construction of the function zeta, which we constructed with the help of the function phi and psi, and phi was initial function and psi was a boundary function. So we will take a just a quick look at how we constructed zeta, and then we will go to the proof of this regularity condition. There is a I would say this is a paradox. I have to prove that solution of this heat equation, if it is a smooth solution, the existence of a smooth solution of the heat equation, it means u should be continuous, its first order derivative with respect to t should be continuous, and its second order derivative with respect to x should be continuous. It means u is belonging to c1 to omega t, where omega t is defined as omega cross 0 comma t. So this is time and this is spatial domain. So this is the domain of the dependence of the heat equation, and u is belonging to c1 to omega t. It means that u, the second order derivative of u is continuous in the given domain, inside the domain. We are not talking about the boundary. We just have one information on the boundary, that u should be continuous on the boundary, because we can't talk about the differentiability of u on the boundary. So in view of this, we define, just let me take a screenshot of this figure because I don't want to plot it again. Oops. So this was the parabolic cylinder. Since we know that this heat equation is a parabolic equation, so the variation of heat which is defined by this equation is going to vary over a parabola, and we are talking about the cylinder because we assume that the flow of the heat is in a either it is in a vertical cylinder or it is in a horizontal cylinder. It depends on you which what you are taking. So here we are taking the vertical cylinder, and since because of the attribute of this solution of this heat equation, it is going to be a parabolic equation, so its solution is going to give us a shape of a parabola. So that's why we are plotting it in this way. Next we define c. This was a parabola. It was defined like this. And the time was varying from t minus r square to t. T was the maximum time and t minus r square was the minimum time. Yesterday I did a mistake. Let's see. T minus r square will come on the bottom and t will come on the, this will be t minus r square and this will be t, because for sure r is a positive number, so t minus r square is going to be less than t here. So t minus r square is going to be time here and t is going to be here. Sorry. Next, we define the sub-cylinder, sub-parabolic cylinder of this C, which was passing through this point x naught t naught. So C x naught t naught r by 2. This was defined as C double dash. This is contained in C dash, that is equals to C x naught t naught comma 3 by 4 r, and this is contained in C x naught P naught R. Just because R by 2 is going to be less than 3 by 4, R is going to be there. So this is defining when you are taking a cylinder. So this is the upper portion is going to be a circle. So R is the radius of the circle. So for sure R is greater than 3 by 2, is greater than R by 2. So because of that it is money. Next we define a function zeta that is defined as phi x psi t. Now, according to the uh, 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 Yvonne, would you please mute yourself? It
Oh
is
yeah, I think it's vibrating my cell phone.
Yeah, I
Sorry.
think there is some issue with your mic, I think. So this was defined as initial condition, like it was given at t equals to 0, and this was defined as a boundary condition. So it was defined on the boundary. Since we are taking a fixed boundary, mod of y minus x is less than or equals to r. So y minus x is less than or equals to r is greater than or equals to minus r. So y is going to be less than or equals to r plus x minus r plus x. So this is the boundary of that parabola. So this is going to be the boundary minus r plus x to r plus x. So this was defined as the boundary condition. So we have a heat equation for which a boundary condition and an initial condition is given. So it has mixed kind of condition, and we define the function zeta phi comma phi into psi in such a way that according to the definition of phi, and I'm not going to write the whole things. Yesterday we saw all the details in the all the this description in the details. So today I'm not going to give you the detail of all these things. So zeta equals to 0 on Rn cross 0 comma T naught minus C, and zeta equals to 1 on C dash, and is lies between 0 to 1 inside of that. Now, next we have to prove that if U is belonging to C1 to omega t, it means the solution of this heat equation is sufficiently smooth. In that case, U is going to belongs to C1 infinity. It means the infinite derivative of U is going to be continuous. The infinite derivative of U is going to be continuous. So that is the thing. Now, what do you understand? What do you guys understand the meaning of paradox?
Paradox.
Paradox, yeah. We use a lot of
Something something that like um defies like the logic,
Mhm.
but like it gives you like a contradiction, a
Exactly.
logic contradiction.
Yeah, logical contradiction. So the statement which contradicts itself is known as paradox. So basically, we are going to we had to prove that u, the infinite derivative of u, is going to be continuous. That is, u is belonging to c1 infinity omega t. So the thing is that rather than proving it, we will assume that u is belonging to c1 infinity, and then we will surplus that things. Okay, so if u is belonging to c1 infinity, in only that case u is belonging to c1 too. That's why u is going to be c1 infinity. This is the way how the regularity condition has been proved. Now we temporarily assume that u is belonging to c infinity omega t. This seems a cyclic argument to what is to be proved, but the following arguments aim to establishing an identity that is valid for C1 to solution. So when we are assuming that U is belonging to C infinity, then we will derive an identity that is valid for all C1 to solution. If we are not assuming that, like the identity which we will derive after assuming that U is belonging to C infinity omega t, that gives us the condition that U will be belonging to C1 to solution. So it is like a cyclic argument. We are not going from here to there, we are coming from there to here. Now let V equals to zeta U on Rn cross 0 comma T naught, then V is belonging to C naught infinity Rn cross 0 comma T naught because of the this zeta. Zeta is bounded function, zeta is a continuous function, so it is going to be belonging to C infinity. It will also becoming a bounded function. Then V is belonging to C infinity Rn cross 0 comma T naught, and as we know that this zeta is going to be 0 on this set, so V and V equals to 0 on Rn cross T equals to 0. Furthermore, Vt minus Laplacian of V. So this will be coming as zeta u. I will tell you how it is coming. Minus t zeta u du minus u Laplacian of zeta. So when you will be taking it like V t equals to zeta t u plus u t zeta, Laplacian of V is equals to Laplacian of zeta u plus zeta Laplacian of u. Here you will pass one derivative to zeta, so it will be like d of zeta d of u, or yeah, we are representing it with t. If we will be in one dimension, so we can say that with the argument and then u over del x with the argument. But since we are in a dimension, so and it will bring a negative sign. So if you will use this property here, it will be now. We are not saying that V is a solution of the heat equation. We are just saying that V equals to 0 on this boundary and V is a bounded and continuous function. So if we take in account that V is a bounded function, V is belonging to C infinity, then Vt minus Laplacian of V is going to be some function that will also belongs to C infinity, because V is belonging to C infinity. So its derivative with respect to t and its second order derivative with respect to x is going to belongs to C infinity. Suppose this is equals to some function f tilde. Now by the property that V is belonging to C infinity, this f tilde will also belongs to C infinity with the property f equals to 0 on this set in Rn cross 0 comma T infinity. Note that f tilde is C infinity and equals 0 on Rn cross 0 comma T naught minus C. Why this is 0 on Rn cross 0 comma T naught minus C? Because according to the definition of zeta, zeta equals to 0 on Rn cross 0 comma T naught minus C. So as soon as you will be using this property, what will be your V? V will also be 0 on this set, isn't it? And then its derivative will also be 0 on this set. And what is its derivative and its difference? This is equals to f tilde. So using these things in our mind, f tilde will be 0 on Rn cross 0 comma T naught minus C. We are taking this closed interval 0 comma T naught because we have V equals to 0 on Rn cross T equals to 0. That is basically initial condition. So that's why it is closing here. And then we were going to take it open interval 0 comma T naught. Hence, moreover, V is bounded on Rn cross 0 comma T naught. Hence, by the uniqueness of the bounded solution, hence by the uniqueness of bounded solution, we have V x comma t is equals to 0 to t, 0 to Rn, phi x minus 1, t minus s, f tilde, y comma s, dy ds. Basically, this is going to be do you guys remember the non-homogeneous heat equation? Ut minus uxx, like ut minus Laplacian of u equals to f, and then we have the initial condition, some initial conditions. So that was supported by a heat kernel. So that was basically giving us the uniqueness of the bounded solution. So Vxt can be written in this form. I would like to ask you one thing. When you are studying a topic like all the subjects include some theoretical things and some geometrical things. So, which way do you prefer to understand the geometrical meaning, like the way of applied kind of mathematics, or the way of pure kind of mathematics?
I prefer applied mathematics.
Yeah, the same.
Okay, because I always teach in the way of applied mathematician. I just state the theorem. Like if you were gonna study this subject with the pure mathematician, then he or she was going to explain you the mathematical pure mathematics thing. But I'm not sure about the geometry. I prefer to be more geometrical. Like I prefer to be more applied kind of things because I am an applied mathematician for sure. So everyone has their own way of teaching style. Like I can explain physics better than mathematics. So given any x comma t is belongs to C double dash. Now if we use the property of xi equals to 1 on C dash, so xi equals to 1 on C double dash, and when as soon as we get xi equals to 1 on C double dash, so using the property v equals to zeta equals to 1 on C dash and zeta equals to 1 on C double dash, so v will be u on C double dash. Now I would like to ask you one thing. Mistakes. Since u xt equals to vxt, it follows that u x comma t is equals to integration over c phi of x minus y comma t minus s f tilde y comma s dy over dx. U equals to v is going to be equals on c double dash. So we have replaced this v with the u, and this is equals to integration c phi x minus y t minus s. It is 0 and c and zeta is also 0. And this f tilde y c y s equals to, I will explain the expression, just wait for a minute. This f tilde is equals to this quantity. Now since it was replaced with y and s, so t is going to be s zeta s u minus 2 d xi into du minus u d xi dy ds. That is going to be equals to c phi of x minus y comma t minus s zeta s plus Laplacian of zeta. Take this term zeta s u minus u Laplacian of zeta. And u y comma s dy ds plus 2 dy phi x minus 1 y t minus s d zeta u y s dy ds. Now you need to pay attention to the second term. See, here it was minus 2 d zeta du, and this phi was free from the derivative. Now we know that the zeta is 0 on the boundary of c dash, it is c dash. This zeta is 0, no, this is c. This zeta is 0 on the boundary of c, and also it is defined inside the domain. So using that property, when we pass the derivative to the second function, so it comes minus with that uh, shifting the derivative. This minus comes with the shifting the first derivative. Minus 1 to the power 2 will come if you shift the 2 derivative. So I am just shifting one derivative d of u to phi. So the minus will be coming, and this will be plus of 2 dy, and this will go, and u will left as it is. So u y comma s dy ds. That is equals to integration over c phi x minus y comma t minus s. In your notes here I have written plus, so that was a just mistake, typos mistake, so please correct it. Plus 2 dy phi x minus y comma t minus s dot d zeta u y comma s dy ds. If it is satisfying on C, then it will also satisfying on C minus C dash, and as per my opinion, I feel that we don't need to write it C minus C dash. It could be C is fine. That if it is satisfying on C, then it is going to satisfy on each subdomain of C. So C minus C dash is basically a subdomain of C. So whether you write it C minus, I just took this notation from the book and then I was reading and I thought that it should be better to write C rather than writing C minus C dash. So take this term as gamma of x comma y comma t comma x, that is the heat kernel. It will be integration C gamma x y t comma s u y comma s dy ds u x comma t for all x comma t is belongs to C dash. Here we were taking this property for all x t belongs to C dash. Now, one thing which we need to keep in our mind, that when we talk about the solution of the heat equation, the solution, the second order derivative is continuous. We say that the solution can be uniquely represented in this form. Now, if we are taking that u is belongs to C infinity, then we are deriving these things without taking any restriction on the boundary, without taking any restriction on the boundary or its derivative. So it means when u is belonging to C infinity, this expression is coming automatically. We don't need to use the Wheeler's theorem. What was the Wheeler's theorem? Anyone remember? So the Wheeler's theorem was that u is a non-negative solution of the given heat equation. Then we can express in this form. And before that, strong maximum principle was saying that we can express the solution of the heat equation in this form when we have the bounded boundary. Now here we can see that if u is belonging to C infinity, then we don't need to take any kind of restriction, neither the non-negativity of u nor the boundedness of the boundary, neither the non-negativity of u nor the boundedness of the boundary. It means when u is belonging to C infinity, we can relax these two conditions and we can express u in the form of the heat kernel. It means its initial data, or you can say that it's boundary data. It is not basically initial data. It is a mixed kind of data. U comma x is given. So in that case, if u is belonging to C infinity, automatically we are able to express the solution of the heat equation in this form, and it requires that u should be C1 function, C1 function, like the second order derivative of the u should be continuous. It means this is implying this condition without any this kind of restriction. So this was the cyclic argument the author took to prove this. Yeah, but like this is like a paradox kind of proof. We are assuming the results and then we are proving the solution. So this was the last topic of your heat equation, and here we are finished. Now I will start the hyperbolic PD, and at the same moment I would like to ask you, please try to complete the heat equation by this weekend, so that in case if you guys have any doubts, we can discuss it on Monday. And you also have the assignment, and I have given some sufficient question to be engaged. So third, we have, I'm just writing the assumption. I'm just writing the thing which I explained. We have derived the identity 6 under the assumption that u is a C infinity solution of the heat equation in the domain using the standard modified technique. The formula is valid for all C1 square omega t, and we don't need to put any restriction on the on the positiveness of the solution or on the boundary. Yeah, so that is the thing you have written in your notes. Now I would like to take a quick look over this heat equation, what we have studied and what topics we have covered in the whole. Just let me open the syllabus and then I can take a quick
Unsteady.
look and I can give you a brief details what you need to keep in your mind. So we have talked about the fundamental solution, the fundamental solution of the heat equation. Can anyone tell me what we did in the fundamental solution of the heat equation?
You use the scaling of the
Mhm.
time. See,
Yeah, tell me, you are right. Just continue rescaling and then
you get two differential equations and you solve it to find the fundamental solution of the.
exactly. So what we did the rescaling, and the rescaling was very important because t has one derivative and x has two derivatives. According to that, the rescaling was something like alpha t comma alpha square x kind of things, and rather than taking it alpha square x, we took alpha t and beta x, and then we derived the solution of the given heat equation. For deriving the solution of the given heat equation, we came across two ordinary differential equation, and to solve those two ordinary differential equation we have to put some restriction on the beta, like it might have 1 by 2 something, and then the one ordinary differential equation was solved, and then using that we solved the second one. So we got the solution in the form of the integration. Now we say that if we are getting the no, we get the solution, and then we say that this form should be exponential of something, and this exponential was a normalized function, and then we call it this exponential form as the heat kernel. So this was the first topic which we discussed in the first class, and it was very easy, isn't it? Do you guys have any difficulty in that one? Okay, then we solved the initial and boundary value problem. Then we came across the weak maximum principle and strong maximum principle. So before proceeding to the strong maximum principle, there is a mean value property which you have to study. So we write the solution of the heat equation in the form of 1 over something volume of something and integration of volume of B and volume of delta B, like that. But for the heat equation it was a little bit different. We use the mean value property to write the solution, and then using this mean value property we proved that the solution of the heat equation is going to be unique in the case when we have bounded boundary. Uniqueness of the heat equation. So what we assume that u and v are two solution of the heat equation given by ut minus ux equals to 0 and u of x comma 0 equals to z. Then we assume w equals to u minus v, and at x comma 0 w is going to be 0. So we have a fixed bounded boundary and w equals to 0 on that bounded boundary. It means the maximum and minimum are going to attain at the boundary. So maximum is 0 and minimum is 0. It is giving that the solution is going to be 0. So u equals to v. This was your uniqueness of the heat equation when we have a bounded boundary, and where the bounded boundary is playing the important role. It is playing the important role in using the strong maximum and minimum principle, isn't it? So the assumption of bounded boundary is basically giving us the power of using the strong maximum or minimum principle. So this bounded boundary, it means you can use the maximum or minimum principle. If you don't have a bounded boundary, you cannot use this. Next, we came across the Wider's theorem. The Wider's theorem is stating that if you have a non-negative solution of the heat equation, if you have non-negative solution of the heat equation, then the solution is going to be unique, and uniquely it can be expressed as integration over k x comma t something and u initial data d of x. So this was the Wider's theorem. What was the necessity of the Wider's theorem? the non-negativeness of the solution of the heat equation. Then we came across the Duhamel's principle. That is the most important thing. Would you please explain me what is the Duhamel's principle?
We can express the solution of a non-homogeneous heat equation in terms of a solution of the homogeneous heat equation, something like that.
Yeah. So we have ut minus uf, a non-homogeneous heat problem with the homogeneous with the zero initial or boundary data. What we did, we assume that we are changing the coordinate, we are changing the variable to u to v, and it change your non-homogeneous heat equation to the homogeneous heat equation. However, your initial data becomes this. Vx comma s equals to f of s, and then we proved that u is nothing but integration of v. This was the Duhamel's principle, and we saw that this is holding, and it was a very easy topic. I think Duhamel's principle was the easiest one. Next, we proved today the regularity condition. I think that is the whole heat equation, isn't it? So this was a brief summary of the heat equation. If you have any doubt in any of this, did you guys read the Wider's theorem yesterday? No. Please read the Wider's theorem, and if you get any doubt, then please do ask to me. You know the basic concept behind the Duhamel's principle, Wider's theorem, the strong maximum principle, and the fundamental solution of the heat equation and the regularity. Now you just need to go through the derivation. You know the basic concept. What is the condition which we needed to prove these things? You know. I believe that you know. Tomorrow I will be starting the wave equation, and the wave equation is the easiest one in all your syllabus, according to me. Let's go over the conservation law again. So in the conservation law, basically we talk about a number of physical phenomena. A number of physical phenomena are modeled by the first order partial differential equation, first order Cauchy linear partial differential equation. So what is the conservation law? Before coming to the partial differential equation, we will take a look in more physics. So according to the conservation law, if you take any domain where the solution is defined and some, say u is the quantity, that is an unknown variable that is changing with time and space. So it is depending on two coordinates ut comma x. Now the temporal rate of change of u, temporal rate of change of u means the rate of the change in u with respect to time. The temporal rate of change of u in any fixed domain omega is equals to the total amount of u produced or destroyed inside omega and the flux of u across the boundary delta omega. So the amount of u which is created or destroyed inside the domain omega, if the amount is created inside the omega, so it will works like a, if some amount of u is created inside the omega, then what you call it source. And if it is destroyed inside the omega, it means some amount is coming and it is sinking. So in that case, it calls sink. And the amount of u, the flux of u across the boundary, the flux of u across the boundary. So across the boundary, what volume is going outside, what volume is coming inside, that is basically known as the flux of the function. It means the temporal rate of change of u depends on two quantity, the amount which is created or destroyed inside this omega. This is omega and this is basically the boundary. And the flux of u across the boundary of omega. So that is change in u is due to two factors, the source or sink. Basically source is created, so sink is destroyed. representing the quantity produced or destroyed, and the flux representing the amount of u, that either goes in or comes out of the domain. So that is basically known as the flux. If a quantity is coming or going through the boundary, so basically we say that there is a change in its volume. That's why ut is proportional to gradient of u. No, gradient of u, volume. So this was the conservation law. In the more mathematical way, it can be written as, if you take u, the rate of change of u inside the domain omega. So the value of u, if you are measuring it, so it is covering all the area. It means integral over u. That is the whole amount, integral of u on this domain omega. That is the whole amount which is covered in the domain omega. What is the meaning of integral? If you integrate, so you say integrate from a to b, then you say that the area lies inside this curve. So if you are taking the integral over this omega, it means the area, it means the quantity which lies inside this omega. So integral of u over omega, we will taking integration with respect to x. The temporal rate of change of this quantity is equals to delta omega, the flux of u, that is depending on u, the flux of u, which is either goes inside or the goes outside. For most of the cases, we assume that it goes outside. That's why we use the outward normal vector. So that's why negative sign comes. Most of the time, we assume that suppose there is a heat which is spread inside this. So most of the time, if the layer of any pipe is not isolated, so the heat is going to be outside of that pipe, isn't it? So it is just a physical assumption that we take that flux is basically coming out of the domain. It is just a physics. In most of the physical phenomena, it happens. So that's why we take this negative sign. And the source, the amount which is created or destroyed, that is either source or sink. So if it will be source, S will be greater than 0, and if it will be sink, S will be less than 0. So this was your conservation law. Is it clear? Now here we use the Gauss divergence. This was a surface integral because we were taking, and then we use the Gauss divergence theorem, and then we write the conservation law ut plus divergence of f of u is equals to s. You guys are very much smart to do that. Next, we are going to talk about the discontinuity in the solution of this conservation law. The discontinuity arising in the solution of this conservation law. So this was the most important thing. I think everyone was confused at this point. So we are going to discuss that how we are talking about the discontinuity. So when I say that scalar conservation law, it means we have only one equation. Another, it is system of conservation law. So keep in your mind, scalar means you have only one conservation law, one equation representing that conservation law, and if you have a system of conservation law, then you have more than one equation. And suppose you are in one dimension, just make it very easy. So that divergence is basically the spatial derivative of the flux function f. And suppose there is no source or not sink. Now, under what condition we can open this derivative? In the case when u is assumed to be the smooth solution, it means its time derivative with respect with respect to x exists. In that case, we can open this equation. So it can be written as f dash of u of x equals to 0, isn't it? Now assume that this is something a. Equals to 0, where a of u equals to f dash u. Now there were two cases. We were very much interested in the only convex flux function. So this is your flux function. In what condition it will be a convex flux function? When you have double dash greater than 0, it means a dash u, that is basically f double dash u. This is greater than 0. It means it is convex. And when a dash u is equals to f double dash u, this is less than 0, this is concave. This plays a very vital role in the definition of the discontinuity of the solution. When we will be proceeding towards the geometry of those solutions, then this plays a very important role. So this thing you need to keep in your mind when we are talking about the convex flux function and when we are talking about the concave flux function. So convex means f double dash u is greater than 0 and concave means f double dash u is less than 0. Now, just give me 2 minutes. Just 2 minutes. Is equals to c of x, and that is equals to u naught x. It means the behavior of this function c is the same as the behavior of the function u naught. If u naught will be a sine function, then c will be a sine function because we both are playing the same role with the same argument. So you can say that u t comma x is going to be u naught. Now just change the argument of this function u naught. So the argument is x minus a u t. It means you are deriving the solution of the given partial differential equation with the condition that this is not an explicit solution. The solution is coming as an implicit function. What is the meaning of implicit function? U is depending on u. So this is an implicit function. If this a of u is a constant function, if suppose this f of u is equals to a constant, rather than saying a, write c naught u. In that case, what will be a of u? This will be c naught. In that case, this solution will be u naught x minus c naught t. It means we are getting an explicit solution, and that explicit solution was representing the solution of the transport equation. Like if you take a color pollutant, you drop on the surface of a river, then it is transported with the same velocity c naught. But in this case, if f is a non-linear, here f was a linear function of u. If f is a non-linear function of u, in that case we are unable to derive an explicit solution. We are getting an implicit solution, isn't it? Now, what will happen when we are getting an implicit solution? So let's talk about whether it is satisfying back to the differential equation and under what condition it satisfies back is smoothly. Under what condition it is a smooth solution of this partial differential equation. So let's have a look at that. So this was u t comma x is equals to u naught. So its time derivative will be u naught dash, that suppose this is xi. You already know this is xi. So the derivative of u naught with respect to xi, and then the derivative of xi with respect to t. So the derivative of xi with respect to t will be, firstly you will derive this function minus a dash u with respect to u, and then ut, and the next part a will be same, and the derivative of t is 1. Now just pass this term to the left hand side. So ut plus a dash u naught dash. Since u equals to u naught dash, so it doesn't matter whether you are writing u naught dash or a dash u. It is just your point of view, how you are seeing it. Ut is equals to minus of a u naught dash. Just take ut outside and send the rest to the denominator of this. So I think I am right. A t will be coming as well, isn't it? Here I am missing the t. Please follow up the derivation, and it should be very clear. It is the main ingredient in the deriving the discontinuous solution. So, and the ux, if you will be deriving the ux, so you are going to get u naught dash t a dash u naught dash. Now, under what condition it will be a smooth solution of the given differential equation? Under what condition u will be a smooth solution of the differential equation? If this is continuous and this is continuous, isn't it? But as soon as this denominator becomes 0, we will lose that convenience, we will lose that continuity. It means in the case when 1 plus t a dash u naught dash is 0, we will lose the smoothness of the solution. Now we know that t is a time. T is a time. So if this quantity is positive, then everything is fine. The only condition will be when this quantity is negative. The only difficulty will be when this quantity is negative. So t is equals to minus 1 over a dash u naught dash. So when this quantity will be negative, the whole quantity will be positive. It means we are going to get a time. But if this quantity is also positive, so there is no negative, there is no concept of negative time, isn't it? Now, what condition we have given? We have two conditions. Just be very careful here. It is very easy but very important. We have one condition, a dash u is greater than 0. And what does it mean? A dash u is greater than 0 means convex flux function, isn't it? Now, if you have a convex flux function and u naught dash needs negative, it means if you have a convex flux function, then the discontinuity will arise only when you have monotonically decreasing initial data. U naught dash is less than 0 means monotonically decreasing. It means case first. I am discussing the case when discontinuity arises. For the continuity, you are very smart. You will just opposite it. I am talking discontinuity arise when a dash u naught dash is less than 0. Now, in what condition it will be less than 0? If you are taking a dash u is greater than 0, so u naught dash has to be less than 0. It means a dash u is greater than 0, convex flux function. It means in the case when we have convex flux function, our initial datum should be monotonically decreasing, isn't it? However, just oppose this condition. If a dash u is less than 0, what does it represent? Concave flux function. So what will be the condition for the initial data to get a discontinuous solution? U naught dash should be greater than 0. It means when we have a concave flux function, then the initial data should be monotonically increasing, isn't it? monotonically increasing. It means forget about the concave flux function. We are not interested in the concave. Just keep in your mind when you have a convex flux function, because the whole theory which we have discussed for the convex flux function. So when you have a scalar conservation law, let me write it in the sentence. When you have a scalar conservation law with convex flux function, then we will have a smooth solution. I will ask only to Yvonne, if you have a convex flux function, then we will have a smooth solution when the initial data is
Decreasing. Yeah, right? It has to be like the opposite.
for the discontinuous. I am talking about we will have a smooth solution. It means this is positive. A dash is greater than 0, so U naught dash also need to be greater than 0. Oh my, you're again confused here. Shall I again repeat it? The same thing? Okay, let me repeat it again and then we can go over that. So I am saying that you are going to get a discontinuous solution, a non-smooth solution when t equals to this. Now t is a time. So at what condition you will get a positive time? When this is negative, isn't it? When this is negative, now we are taking a convex flux function. Convex flux function means a dash u, that is f double dash u, is greater than 0. So this is claimed to be greater than 0. So what is the condition to non-smooth solution? U naught dash should be negative, is not it? And U naught dash is negative means decreasing, monotonically decreasing, isn't it? It means just reverse it. We will have a smooth solution when the initial data is monotonically increasing. What will be the reverse of this? Monotonically increasing. So we will have this, again we will go through the geometry, just wait, this is a mathematical thing, we will go through the geometry as well. So we will have a smooth solution when the initial data is
Monotonically increasing. Yeah.
Exactly. However, we will get a discontinuity in the solution when the initial data is monotonically decreasing. Now, is this part clear? Let's go through the geometry of this. So, what is the meaning of along this characteristic dx over dt equals to f of u, f dash of u, that is basically a of u. The solution u is going to be constant. It means if we plot u is constant, means these are going to be straight lines. These are going to be straight line. It means along each straight line, the solution is constant. But it might be possible that these two lines, what will be the condition we are getting a discontinuous solution? It means at a single point you are getting two solutions. That is, the solution is overdetermined. So the discontinuity will be like one characteristic is emanating from here and the solution u is constant, say it is u1. And one characteristic is emanating from here, say along this solution is constant and it is u equals to u2. So at this point, you are getting two solutions. One is U1 and one is U2. It means the solution is overdetermined. The solution is overdetermined. It means we are unable to find a unique solution because two characteristics are intersecting. Two characteristics are is this geometry is clear or not? Shall I take another method to explain this? Is it clear, Ivan? It means when two characteristics are intersecting, in that case, we will be getting a overdetermined solution. It is not a smooth solution. That is, we will getting the non-smooth solution. Now, when two characteristics will be intersecting, that is the point we need to discuss. So this is the most important thing. Just let me copy and paste it on the next page, and then we are going to talk about this. Just keep in your mind the convexity of the flux function. The convexity of the flux function. So, if you notice, then this was x-axis and this was t-axis. And if you draw a line, then how you decide what will be the angle of that line? You decide the angle of that line. Suppose I am drawing a curve. I am drawing a curve in x versus y axis. Then how we decide the angle, in which direction the curve will be? Suppose this is a straight line. So we say that dy by dx equals to tan theta. Isn't it? So this dy by dx, that is also known as a slope of the curve. This was a straight line, so it was a very easy. But suppose if you are drawing a curve, then at every point you draw a slope. Here the slope is going to be greater than 90 degree. Here the slope is going to be less than 90 degree, and which is parallel to x-axis. The slope is going to be infinity, isn't it? So you draw this straight line with the help of the slope. Now you know that what will be the slope for x and t? dt over dx. Be very attentive here. It is a very small detail but very important. dt over dx is the slope of the line, and this is equals to tan theta. Now take 2 points x1 and x2. Now I am going to draw it exclusively to show it to you. So draw, this is suppose x1 and this is suppose x2. According to the x-axis, x1 is going to be less than x2, and this is your t-axis. Suppose one line is emanating from here. Now if x1 is less than x2 and f dash is f is a convex flux function. F is a convex flux function. It means f double dash is greater than 0, isn't it? Now to get a discontinuous solution, what was the necessity? That u naught should be monotonically decreasing function, isn't it? And if x1 is less than x2 and u naught is monotonically decreasing, then what will be the relation between u naught x1 and u naught x2? Yvonne.
U0 of x1 will be greater
Then u naught x2, and f double dash is greater than 0. It means a dash of u is greater than 0. So this is a monotonically increasing function. A is a monotonically increasing function. Sorry, a dash is a monotonically increasing function. So u naught x1 is greater than u naught x2. So what will be the value of f dash u naught x1? What will be the relation between f double dash u naught x2?
Less.
This is monotonically increasing, so this is greater than this, so this is going to be greater than 0 because we are calculating the value at u naught, isn't it? Now f is a function of u. So this. Is this point is clear or should I explain it again? Clear? Or you can
Yes.
definition of the convex function, but since we also have a dash u is greater than 0, so u is the argument. Don't focus on the x1 and x2. U is the argument now. Now u1 is greater than u2. Say this is u1 and say this is u2. So using the property of the monotonicity of A, we can say that A of u1 is greater than A of u2, not f dash, because A is monotonically increasing. A is monotonically increasing. And what is A? F dash. So we will put the condition on F dash. Sorry for that. So F dash u naught x1 is greater than F dash u naught x2. Is this point clear, Roberto? Yeah. Yeah. Okay. That was the point. Just keep in your mind x1 is less than x2. Now you have three relations. A that is depending on u and u that is depending on x, isn't it? So when you are playing the part of x1 is less than x2, so firstly you will go over u, isn't it? So in the case when x1 is less than x2, we will go over u naught. U naught is monotonically decreasing. So using that property, can we say this thing? U naught x1 is greater than u naught x2, using the property of monotonicity of u naught. Okay, just let me erase it and again I can explain it. X1 is less than x2. That's clear? Now f double dash of u, that is basically a dash of u, that is greater than 0, convex flux function. Now to get a discontinuous solution, what is the condition? U naught dash of x should be less than 0. It means u naught dash x is monotonically decreasing, isn't it? Now when u naught is monotonically decreasing, x1 is less than x2, so what condition will be coming on u naught x1 and u naught x2? The property of monotonicity of u naught will give that as soon as x1 is less than x2, u naught of x1 is going to be greater than u naught of x2, isn't it? Because it is directly depending on x. Now, when we are talking about the monotonicity of A dash u is greater than 0. It means A is monotonically increasing. A is function of u. A is function of u. So u naught x1 is greater than u naught x2. What you can say that A u naught of x1, A u naught of x2. Say this is u1, this is u2. So this is making you confused. So talk about, because we always talk about the augmented function. We don't go over the intermediate function. We talk about it directly depending on it. So u1 is greater than u2 and A is monotonically increasing. So can we say that A u1 is greater than A u2? So that is saying that A of u naught x1 is A of u naught x2 and A of u naught x1 is f dash u x1 f dash u x2. Now is it clear, Roberto? Okay. Now when we are plotting the characteristics line, then dt over dx1, dt over dx at x equals to x1. What it will be? It will be 1 over f dash u of x1, isn't it? And dt over dx at x equals to x2 is equals to f dash u of x2. Now just keep in your mind that you have f dash ux1 is greater than f dash ux2. So 1 over f dash ux1 is going to be less than 1 over f dash ux2, isn't it? It means this slope is going to be less than this slope. So if you are drawing a line at x1, so this tan theta, this theta is going to be less than the theta at this one. It means if suppose this is theta 1, so theta 1 will be less than theta 2. Now theta 1 is less than theta 2, so theta 1 will be going like this and theta 2 is greater, so it will be slightly like this. Isn't it? So it means you can see it geometrically that these two characteristics are intersecting. Is it clear, Yvonne? I will not proceed with the Riemann problem. I would like to ask you, you guys have a WhatsApp group. Please discuss these things in your WhatsApp group. Try to study and do it today. Please. I am requesting all of you. This is the most important part. If you understand this thing, you are pro in solving a hyperbolic PDE. At this point, if you have any small doubt, then please do ask to me. So please, you have two things to study. The first thing, convex flux function. Discontinuity will be coming when initial data is monotonically decreasing. Smooth solution will be coming the initial data is monotonically increasing. Now, this was the mathematical theory. And we can see it geometrically here how the characteristics are intersecting. Now, if you get any doubt, it is your homework tomorrow. Like this today, please read this thing. Please. Yeah. So I'm stopping here. If you have more doubt, then tomorrow I will start the wave equation. But after starting the wave equation, in the last 30 minutes, we will discuss the rare fractional shock wave solution. Okay. Okay. So see you tomorrow. Yeah. Bye.
Bye.
Bye.